Good morning, everyone. I will talk today about cold oxidation as an air treatment techniques, specifically applied to potato processing and more applied to the control of aldehydes. My name is Preben. I work for Olfasense in Belgium, and it's research we did together with Ghent University, and Lien helped us with this. So our Belgian fries, they have a bit of an issue. In Belgium, the Sector Federation claimed that 6 million tons of potatoes were processed in 2023, and about 3 megatons of frozen fries were exported in 2024. And this makes Belgium Europe's #1 exporter of frozen potato products. But it comes with a big marketing issue. Everyone is still calling them French fries, but if you look at the table of mass of processed potatoes, we see Belgium is processing about 4 times as much potatoes as France, which is why I'd like to take the opportunity for a rebranding and come up with Belgian fries instead. But all jokes aside, the issue is obviously an odor issue. So Belgium is quite a small country, and we're processing a lot of potatoes, and especially in the western region of Flanders, and there's a strong presence of potato processors. And these processes typically come with large waste air volumes, which can cause some nuisance for neighbors. If we look at the potato processing, it consists of several process steps. So the washing, peeling, cutting, blanching, drying, frying, oven, weighing, and packaging. And all of these processes, they have their own odor contribution or contribution to the odor emission, as we can see in the table here. So from our previous studies done for these types of companies, we actually came up with a table where we see that drying and cooking are the most important contributors to the total odor emission. The typical odor of a potato processor consists of a lot of saturated and unsaturated aldehydes, which cause this fatty and greasy, sometimes even grassy odor. And these compounds typically have very low odor threshold values, like below ppb levels, which makes them quite hard to get rid of. When we look at the European best practices reference document, actually 3 techniques are proposed specifically for potato processing. It's thermal oxidation, biofiltration, and cold oxidation. And it's the latter we're going to talk about today. So cold oxidation or non-thermal plasma, the 2 terminologies are used interchangeably, is actually a fully or partially mostly ionized gas at plus-minus room temperature. And typically using electrical fields and alternating current fields to generate a plasma. And plasma consists of radicals like hydroxyl radicals, but also ozone, which are supposed to oxidize the odorous compounds in our waste air gas stream. And it's important to note that a few configurations exist commercially. I think the most used today is the bypass configuration or the injector configuration, which uses a plasma module which generates the plasma outside of the waste air stream and then injects the plasma into the waste air. On the other hand, you have the inline configuration where the plasma is generated inside of the waste air. There's also some different options concerning the geometry of the electrodes, and big advantages of cold oxidation are that it's quite a compact way to treat very large air volumes. Like you see here, it's a really compact setup. This is a typical bypass configuration. These installations are quite energy efficient. You put in some electrical energy, but you don't require any chemicals, and there is actually no waste generated. So for the study, our research goals, we observed from field observations and from our studies that sometimes cold oxidation works really well, and sometimes it doesn't work at all. And we didn't have any clue why. So the research goals were to identify and to quantify which parameters control the removal efficiency, and then to see how these parameters and how this odor abatement scales on an industrial level. So we went from a lab scale environment to pilot scale to full scale in one study. So you see the flows as well. And we wanted to focus on aldehydes because we already knew that these are very present in the potato processors, airstreams, and also these are quite hard to remove and to fully oxidize. So they're quite interesting to study, but it also makes that this is not, this doesn't take into account the complete package of compounds in the air. The study was performed together with the commercial cold oxidation equipment supplier, which I will not try to name, and an industrial potato processor. So starting at the lab scale, we could use a very small plasma generator, which they typically use for a first test, and it was an injector type of module, so bypass configuration, where you take some injector air, you run it through the plasma module, it generates the plasma and injects it in the waste gas line. And the waste gas was artificially generated in the lab, so we had complete control over the concentration of two aldehydes. We used nonanal and trans-trans nonadienal. And we could also vary the humidity of both streams, so of both the waste gas and the injector air. We could also try several power levels for the plasma module, and the result was collected in an elephant sample bag, which we continuously measured using online MS. So we get real-time results because we use this SIFT machine. So when we look at the results for the lab scale tests, we actually found out that rather long contact times were required, so up to 20 minutes to get decent removal rates, which is not realistic at industrial scale. And then we also found a very strong dependency on humidity, which is shown in this graph here, where the blue line is the average of all experiments performed at low humidities on both airstreams, while the orange line is with both air flows at 50% relative humidity. So you can see when both streams are dry, removal occurs a lot faster. And this is related to radical stability and also shows as higher ozone concentrations when the relative humidity is lower. And we also saw that nonanal showed higher removal or faster removal compared to the saturated aldehydes, which was probably related to the fact that trans-trans nonadienal is a conjugated system, so it makes it chemically a bit more stable. But also the concentration of nonadienal, the starting concentration was lower, because of experimental conditions, which might have also had an effect. So then we move on to the pilot scale. The pilot scale was conducted at the potato processor in Flanders. And actually we used an airstream which was branched off the stack which contained room air and air from the fryer area, but not the air from the fryer itself, because that airstream is treated with thermal oxidation. And what's quite interesting is that this airstream is already treated under normal conditions using a full-size industrial cold oxidation installation. But for the study, of course, we turned it off, but it made that we could compare the full scale directly with the pilot scale on the same airstream. And during the study, we wanted to take what we learned from the lab tests to pilot and full scale, so we want to check residence time and the effect of humidity. Analysis was done by olfactometry and thermal absorption GCMS and also sensory analysis. Because we moved from an online measurement system to offline systems, we had one big issue, and that's the high ozone concentrations in the sample bag we collected, which will change the sample composition over time, and especially during the time from sampling to analysis, which typically consists of a few hours. The sample can be altered pretty badly. Previously, we used to inject ethylene into the sample bag to quickly neutralize ozone, because it's a very fast and quantitative reaction. But the EN norm for olfactometry doesn't allow for adding gases to the sample. And also you form formaldehyde, which isn't very good for your panel. So instead, we developed some ozone denuders, which we developed specifically for bag sampling. And then we did some in-house validation of the sample integrity, and that worked pretty good. In practice, it also worked really well, except for some humidity issues, which can cause plugging. And then additionally, we used something which I'd like to call isotemporal sampling, because we are interested in the concentration of the gases at the end of the stack. But typically your measurement point is not at the end of the stack, it's somewhere in the middle. So we compensate for the time by adjusting the tubing length, but also by adjusting the sample flow to make sure we sample at the correct residence time, so you get a really representative sample. So schematically, it looks like this. It's actually pretty annoying. So this is the full-scale installation where you see the waste gas stream and the stack. So this waste gas stream is 65,000 cubic meters per hour, and you see the plasma injector and bypass configuration here. So for our pilot scale test, we took a small part of the stack. We ran it through a silica dryer, which was not always filled in the same amount. And then ran it through our plasma injector, which is a similar module as the one used in the full scale, where we also had the option to dry the injector air when the air was just emitted. And of course, for the tests, we turned off the plasma injector. Yeah, in reality, it looked a bit more chaotic. So like this, just for the show. So when we look at the contact time, we tested two conditions. So 4.7 and 8 seconds of residence time. So contact between the radicals and the waste air. And then we see if we increase the contact time, we get better removal. So this kind of makes sense, but it depends a lot on which type of compound. So for hexanol, you clearly see much better removal at 8 seconds compared to 4 seconds. For nonanol, there is not that much difference. Butadiene, which is also quite important, so an aldehyde, giving this bakery smell, reacts completely to below the detection limit. But in general, we also see like the total VOC concentration decreased further when we gave it a bit more time to react. This completely makes sense, but also correlates well with previous study and with literature, so that was nice to see. The humidity, the tests for the humidity, there we used 4.7 seconds reaction time, and we actually did 4 experiments showing a bit of mixed results. So in experiment 1, we didn't try anything, and you get about 30% removal efficiency for TVOC. For experiment 2, we dried the injector air, and there you see something really rather special happening. There's aldehydes being formed. But I have to say it's mostly the really typical odor components actually reacted, but they formed smaller aldehydes. That's what you see here. During experiment 3, we dried the waste gas stream. There you get really good, better aldehyde removal. And during experiment 4, so both streams dried, you get the best removal efficiency for your system. Then at the full scale, or when we compare to the full scale, this was relatively humid and also had very short retention time, which led to that no effect was measured for the cold oxidation installation. So to conclude, contact time is really an important parameter or driving parameter when using cold oxidation, which is something you have to take account when you dimension your system. So to really have a few seconds of time for the radicals to react. Humidity is also really important. Your drier air streams show much higher removal efficiency, which is a bit hard because the injector air humidity is an environmental factor, so it might be hard to control. Between the lab pilot and full scale, we discovered no linearity. There were severe differences. So it's annoying. But on the positive side, we showed some really nice development for ozone stripping before sampling in the bag. It still needs a bit of refinement, and we will work on it. And we also like to study the difference within stack dilution, which is also used from time to time. And then two things which weren't studied were the effect of waste gas temperatures. So this is something for the future. And also the difference between different configurations, for example, bypass vs inline configurations for the cold oxidation. So yeah, thanks a lot for listening and for organizing. And if there are any questions, I'm happy to answer.
Many thanks, Preben, for your very interesting presentation. These, let's say, I would call them innovative approaches for the end-of-pipe treatments of odorants are very, very interesting. So let me check if any question has arrived from the YouTube channel. In the case, I have at least two. Okay, now you see, sorry, I had some problems. Spain, okay, but seems that this presentation has not received any question, but I do have one, which is pretty important, which is about the electrical consumption that you think and you, let's say, you project to use per unit of volume air to be treated within your system?
Well, that's it's a pretty good question. I actually don't have the answer for it, so I weren't really involved in the technical design of the equipment. I know they're pretty energy efficient, and it's well compared, and that's their main selling point, of course. Compared to thermal oxidation, the energy consumption is much lower, but there is a lot of solar energy excess. So yeah, that's why they approach it as a very energy efficient technology. But I cannot give you any numbers on the exact power consumption.
Okay, so private expertise from the company, I see. Anyway, of course, it can be a plot twist because this system essentially only needs clean air and electricity in order to reduce the amount of odorant. So surely, with respect to other technologies which do need other raw materials like water, like chemical agents, like activated carbon, can be surely a very interesting solution.